Now directly I want to focus on my lecture. I think this is not a type of lecture. This is a just a discussion with. Okay, this is experiment one. Actually, I think you are seeing this experiment one, measurement of the earth cone distance.
Yes, now we can see full screen.
Okay, okay. Thank you for this cooperation. So this simple, very simple experiment, we know the actual distance between the Earth and Moon, and we know this. But actually, this will be very pleasure for the class 10th, 11th student if they can measure at their home roughly. So just you need a the small telescope. Small telescope means this is a just you can use a finder scope also, means a 6x or 5x finder scope also available for with a telescope. So you can attach a small telescope on a platform, and actually there will be a attachment with a protector. So this mini clinometer in clinometer gives you this result, and we sorry. So I think everyone can be able to build this setup, and just we have to measure the angular size of the moon with this setup. So this will be better if we put a crosshair on the eyepiece of this small telescope to for the perfect measurement. So there is a illustration. Uh, a astronomer viewing the moon with a naked eye. So just uh, put the clinometer, and this clinometer has a small weight mentioned here as a red line, means this is a movable thread with a heavy stone or something. So if we focus, or if we target the moon, actually moon one side of the moon, means if we fixed our crosshair at one side, then at that time we have to record the angle, and again um, uh, tilted up the telescope, and the just feed the crosshair at upper edge of this moon. So we can roughly get the angular distance or angular diameter, just difference taking the difference of two data. So here roughly we this is my data. Actually roughly this is 0.5 degree. So just change the degree to radian, and for a small angle we know theta equals to d by d, just like a sin theta equals to tan theta for small theta. So roughly we have the mm, very close value, 3 lakh 3 lakh 98,000, and we know actual value is 3 lakh 84,000. So actually this is roughly measurement, but result is very close to the actual result. So a student of class 9, 10, 11, 12, also any people interested in astronomy can perform this experiment, and they can enjoy, and we get the better result doing the same experiment again and again, and using the uh, good telescope with a tripod, which have a setting circle there. So we can directly measure the angle from the setting circle. um, so we can perform in better way as you choice, as your choice. And so this is a very simple experiment, but I think uh, a lot of people have a telescope did not perform this experiment also. So I just saying, do this experiment. And a second thing is, we know the orbital path of the moon is not circular, elliptical. So the distance is varying. So the angular size also may be varying for the position. At one closest at closest position, this is 0.56 degree, and at at apogee position, the angular size is 0.49 degree. So you can mm, measure this angle also. Also, you can measure the distance at apogee and perigee also. So this would be also second step of this first experiment. Now we are going to measurement of a size of the crater on the moon. This image I have taken with my telescope. This or 5 inch or means 127 millimeter reflector telescope with my smartphone. So just if you have a small telescope and if you are passionate with capturing the photo of this moon, just like this, not too much clear or too much magnified. This if you have a this potential, then you can measure the size of the crater, means diameter or length, height. So just you need a ruler. Everyone have this ruler and a photo of the moon. So here I have illustrated this thing, and this is my own calculation. There is a full moon image. So just put your scale ruler in front of a crater and in front of whole moon. This is actually I just drawing this line and measured with a scale, just putting the scale or ruler on the laptop screen. But you may good result. We actually if we uh, take a printout of this thing and just measure the diameter with a scale. Here this is 10.8 centimeter. I have measured just putting the ruler on the laptop screen. Without zooming this in laptop, I have measured the diameter of this small crater Plato. So actually printing this image, this gives the good result. In laptop there should be a zoom option. This can be changed time to time. So just print it and take a measurement with your ruler. Uh, I have put here I have measured the diameter as a 10.8 centimeter, and I know the diameter of the moon from previous experiment, or actually you have taken the data from the website also. And this is 3474.8 kilometer, and I have measured the diameter of the Plato crater as a zero point 0.3 centimeter. So just relating these two values, we can get the actual diameter of the Plato. Here Plato diameter is 0.3 by 10.8. Actually 10.8 the diameter of the whole moon. So into multiplied by this actual diameter gives the 96.52 kilometer. And we know actually the diameter of the Plato crater is 101 kilometer approximately. So this is very close result, and actually I have performed this experiment just once. If you perform the experiment few times, I think you will get the closer result of the actual value discovered by the measured by the
to understand what prime numbers are. What are prime numbers? Okay. So prime numbers are those numbers.
Anyone anything, any problem, sir?
Okay, no.
Are you asking something, sir?
No, sir. No, sir. No
please
question.
carry.
Okay. Thanks. Sorry. So this is the there is also a red line you are seeing. This is the Mount Apennine. I have roughly measured the Apennine as a 2.1 centimeter with my ruler, and calculating this thing, I can get the 675.65 kilometer. We know the actual result is 600 kilometer. So this is also very closer, and I think there should be a very much approximate. Actually, this is not actual result 600 kilometer, because a mountain have a just not a actual distance. So this will be fine, I think. Second thing, in the experiment, see the crater's height. We can measure the crater height also. So this is little harder from this previous experiment too. Just I have to take. We have to take the image like this. Means we have to clearly clear image with a clear shadow. This is the very important thing. From the shadow, we want to measure the crater height just like this. There will be a crater. I think I have measured this. Actually, this is not my image. Image is published in BBC Sky magazine. So thanks to BBC Sky magazine. So this actually the crater length is measured with the ruler as a 11.5 centimeter displayed here, and the shadow is 3.5 centimeter. And there also we can measure also peak height, just taking the shadow of peak as a 2.3 centimeter. So actually we need a extra data from a website or a app, Lunar Terminator Visualization tool, and this tool gives the sun angle for the particular time, particular date when we have taken this the image. This is a very important thing. So from this website, the author from this actually this image, I think this image, when this image is taken, I have to find out the sun angle as a 4.87 degree. Also for crater there is a 3.66 degree. So using this thing, just calculate like this. Tan theta, we know tan theta height by base. So using this thing, and we using the angle of sun at that time. So base is the shadow, height is the unknown here. So crater height also we can calculate 2852 meters, 2.8 kilometers. So this is very simple thing. Also here also we have calculate the real shadow length. Sorry. So for shadow length, we can measure the height of the wall, or and from the shadow of the peak, we can measure the peak height. Very simple, and obviously you will ask after my session if there any doubt. So say fourth experiment is the period of rotation of the sun. We know this is a gaseous giant, so period of rotation is not fixed for every portion of the sun. Uh, there will be illustration with for equator. This is 25 days, and to 35 near about the polar of the sun. So we can measure this thing from our home with my telescope, with our telescope, using the or observing the sunspot. So this is the Galileo's work as an example. Galileo drawing of sunspot June 9, 10, 11, 16, 13. You are seeing that there is a red arrows. The sunspot is moving towards right after one day. So just you have to this is the time of the Galileo's time. So now we have a smartphone, we have a small camera, so just take image, but every time you should take the image with the same magnification or same setting. uh, Setting means just there will be two magnification. One is the magnification of the or zooming of the smartphone or camera, another is the magnification due to the telescope. So just keep all these things same for several days, several up to just try this experiment for 30 days. But we have no such time for continuation. So don't worry, just take 2 3 4 photos, just find out the angular shift or the linear shift, just printing out the sunspot, sun with sunspot. And there should be also same the printing properties, means the margin, zooming, etc. So everything should be same uh, in the time of printing. So just there will be two illustration, and just finding out the ruler. The sun diameter is 9.6 centimeter across, and we have to observe 3 or 4 days or 4 images, because we have to also measure the direction of the movement of the sunspot. So just 3 4 5 days, we are able to find out the direction of the uh, movement. So here in a day, that is 13th June, and second image is at 14th June at same time. So at a 13th June, this distance from the one edge, as a we are mentioning here 4111 transport number. So this distance is 3.4 centimeter, and just after one day this is 4.2 centimeter. Just take two difference, and from these two length, 4.2 centimeter and 3.4 centimeter, we have measured at 0.8 centimeter in a day. Or it is not very essential to fix the time exactly same at the 13th June and 14th June. Just if we miss the actual time, then no, don't worry. Just take the difference or take the time in hour, not a day. So let in 13th June I have taken in 8 a.m. and in 14th this is the time is 9 a.m. So this is 23-year gap. So don't worry, just take 23-year gap to move this sunspot from one point to another point. Uh, this is 0.8 centimeter here. Just we have to relate this whole diameter as a 180 degree. So just 180 degree is a 9.6 centimeter. So just 0.8 centimeter is a I have measured here, and sunspot moves 15 degree at 24 hours. Here is a calculation. So just I have measured here for this uh, sunspot. Roughly this region moves with rotate with 24 days. Here this is 26 days, like 26 or 20 or means 20 this region should have the result between 25 and 26 days. So we have measured this is as a 24 days. So this is very fine. Actually this is rough, not a actual data, actual movement. We are novice, we are a school student, we are college student. So this is very fine for the for us. And actually this 24 days, this result is not very much important. Very much important this, we have measured several movement for several sunspot in several region. then we can find out few of sunspot have a movement in 24 days. For few sunspot, this region should have 35 days. So this variation gives the pleasure. We can find out. Second thing is, another interesting is, you can take multiple images for at least 30 days and make a video to visualize the rotation of the sun. But same thing, we have to take the setting same for these 30 days, means setting for telescope and setting for the camera or smartphone. Try to take 5-6 photos in a day. Gives also a good result, means in 30 days, if we click the 100 photos, 100 images, this gives a beautiful videography for this rotation of this sun. So this is a fifth experiment. Fifth experiment gives the period and distance of Galilean moons from Jupiter. This will be performed with very 4-inch or 5-inch telescope, reflector or refractor, no problem. And just we have to take, there will be just remembering, IO Europa Ganymede have a period with 1.8, 3.6 and 7.2 days respectively. So just 1 week, for a 1 week we can measure this distance or period and perform the experiment. Just we have to take a note. Suppose there is a Europa at the left side, and just you have to draw on your notebook, and at the extreme left position you have to take the time and date, and observing the day by day, we have to wait for the Europa at extreme right, and we have to take the result, means take the time and date for the Europa at extreme right side. So I think this should be 180-degree or half of the journey of Europa. So this this will give the for Europa this period will 3.6 days. So we can guess at one and means you have to convert the in days in hour, and we have to take more data. For IO, this is 1.8 days. So we have to we can measure the period and the distance, but we have to measure day by day. Day by day means just we have to perform this experiment for a night also. We can get the result. This is the experiment 6, occultation. Occultation is special event when a bright object, celestial objects obstacle with the moon, and there will be a lot of calendar there, lunar calendar in sky.org, lunaroccultation.com, etc. So from this occultation event, we can measure the moon orbital rate, that is 0.56 degree per hour. Actually, moon is moving towards east each hour at a 0.56 degree. We can measure this. Just we have to take the here is a occultation of Spica, and just at this condition, like this image, we have to take the time and date. Date is not important. This is a few minutes event or few hours event, and wait for total full event, and take the time after emerging from the opposite edge. This should not be just directly opposite, but approximately we can measure the uh, time to travel behind the moon. That is, moon is moving in front of the spiker. So just taking this time interval, and we know this moon diameter is 0.5 degree. So just taking the time and degree, we can find out that this 0.56 degrees per hour. And you know, many of us, you know, the maximum directly means across the moon occultation, uh, maximum time is 1 hour, 1.2 hour, like this. So actually the moon is 0.5 degree and the moon orbital rate is 0.56 degree per hour. So many of occultation takes the time near about 1 hour. So we can measure from our home and for this event we do not need any other special equipment, just a small telescope 70 mm or 80 mm, 90 mm reflector or reflector telescope. Or if for a precise measurement of time, you can use the tracker for the telescope, and you can take the videography. From the videography we can find the exact time in a millisecond also. So we can take the precisely time, and we can measure this angular orbital angular rate. There will be a illustration for if there is a no directly occultation. Direct means, this is not scientific term. Direct means I want to mention here across the moon. So when the occultation of there is a spike occultation means the emergence and the starting point are the not across the diameter. No problem, I just take the value with ruler. This is 6 centimeter from a image, and this the actual diameter is 6.2 centimeter. So we can find out the angle for angular value for 6 mm, uh, 6 centimeter. So and we can perform this same experiment. Experiment 7 is a variable star experiment. This is a very much scientific experiment in scientific community. Scientists are doing this thing, but variable stars, there will be two type of variable: intrinsic, extrinsic. Intrinsic means actually variable star, and this variation of the variable star means there will be a variation in brightness, and it takes more times, few hundred years or few hours also. So many of the variable stars that can change the brightness in few hours, they are not truly by a variable star, they are eclipsing by variable star, eclipsing binary star. So we can measure a variable star in a day or once in our life. So just we have to measure the brightness. So this is visual observation. This is very difficult to us. So there will be a lot of thing, but we need a very special thing. One is a corrected star chart. After launching the app in smartphone or laptop, many of us do not have any star chart, but this is very essential. We need a star chart. Actually, star chart paper star chart has a brightness guide in the bottom. So this is very important, and there will be another important thing is the comparison star chart. Means the star we are going to observe, uh, there should be another comparison star beside or in a field of view 1 degree. Uh, we we have to know the reference star magnitude also. This is a comparison star chart. Here a lot of marking there. This is a 6, 7, 8, 2 or something. Actually this is 6, 7 is 6.7 magnitude star. 8, 2 means 8.2 magnitude star. American Association for Variable Star Observer gives this type of star chart. So they mentioned there will be not a decimal point, but we have to treat 7.1 means 7.1. So if we want to measure the brightness of any of the star, then we have to follow the side by side star reference stars. So we can just like there will be a written 6, 7 means this is 6.7 magnitude. Just below this there will be 10.5 magnitude star. So we can identify the star between 6.7 and 10.5 magnitude. This is very small and smaller than the 10.5 magnitude. So I can think this is a 13.13 magnitude star. So just we need this reference or comparison star chart from the American Association for Variable Star Observer, or also we can download from another type, British Astronomical Association, BAA. So there will be also a star chart. This is a star chart SS Cygni, and this whole thing is a field of view 1 degree. So 1 degree field of view means you have a 5-inch f5 reflector telescope, then at 30x magnification, this gives 1 degree. So magnification is not very much essential if we are observing bright star, but after 6 or 7th magnitude, 6th magnitude, 7th magnitude, we need a special type of telescope, means we powerful telescope with more magnification or more aperture size. So this is not very much. So again, this is also a star chart. This is a comparison star chart. So we need both these two things. So from actually this experiment with a variable star, we have to. So actually this topics is on variable star is very large. We can discuss another day also. So just visit BAA or AVSO website. You can find a great lot of research freely, or you can contribute in scientific community, or you should have a paper or scientific research paper also. So graduate student, MSc student, or amateur astronomers, or give doing this experiment, you can also do at home. So this is my addition using a smartphone. Actually using a smartphone means I am mentioned here is a app PFOX. PFOX is a great app for scientific experiments at home. So there is a lux meter. So using a lux meter, you can also compare the you can check also the brightness of the variable star. The lux value is not very important, but suppose the reference or comparison star have a 10 magnitude, and I have find this is a 7.0 lab. So if we are seeing the unknown variable star and using the smartphone, this gives the 30 lux. So just using these two value we can compare in the magnitude. This is 70 as a 10 magnitude. So just 30 as a different magnitude. So just you can use this lux meter your using your light sensor of the smartphone. So just check it. I think this would be possible. Experiment A is very interesting, measuring the temperature stars. This is actually a rough measurement. So just actually we know the colorful stars have existed. If the star have a blue light, and means this have a higher temperature, and red means a dying star, means a lower temperature. So just visualizing this thing, this is very difficult to identify which is very much red, which is very much blue, and just compare. But if we want the scientific result, then use the three filter: blue, red, and green. So if you use these three filter, and just use this filter and take the brightness with your smartphone, and we have to compare this the intensity of three using three filters, just like this. So this is a graph. This is a graph. So for a graph, we need a stellar spectroscopy. Spectroscopy is very much costly. So we can get rough result. Suppose the intensity is 70 for blue light, or 30 for red light. So we can easily say that this star is a blue star. Blue type star means this temperature is 28,000 to 50,000 Kelvin. So this is a very easy trick, I think, very much easy thing. Or this is spectrography result, and so we are using the Wien's displacement law, and this is a good project for a graduate student also. So for this we student need special guide from the teachers, or we can discuss later. But for a stellar spectroscopy we need a spectroscope. But I performed a experiment with just a grating of cost 500 rupees from Amazon. So this grating also gives you a good result, but I especially unable to see the absorption spectra. But you can see the absorption spectra if you attach a small special telescope, just like a spectrometer. Uh, we can, I think, we can able to see the spectrographic absorption spectra. But I have measured the continuous spectra for Sirius star. So for different star, we can get different continuous spectra. Different means the intensity of blue light, intensity of red light, intensity of yellow light is different, but all are continuous. For just placing a grating in front of the eyepiece of your telescope, and just view. This is actually, in this illustration, this is reflected light from a grating, but you should not observe like this. This is very difficult, opposite direction towards the telescope. So just place the grating perpendicularly in front of the eyepiece, and direct light you will get the white light. But after first maxima, second maxima, third maxima, you will get the continuous spectra. So just take the second or third continuous maxima, and you will get the continuous spectra. Or if I will I asking you, all of the students, you may also perform uh, this continuous spectra for to measure the uh, temperature of the star. Means a image, a continuous spectra have a brighter brighter portion in the blue light. So this is we can roughly treat it as a blue star. but maximum intensity distributed in the red star, so red light, so we can treat as a red giant. So this is a very complicated experiment, but you can try. You can try. This is important. For stellar spectroscopy, this is advanced illustration. If we are able to buy a special type of spectrometer for the stellar spectroscopy, then we are able to see the absorption spectra. There's a black line in this image. And so for from this absorption spectra, we can determine the uh, elements in front of the star, that is the star light coming through a nebula or something. Then we can identify the material or element in the nebulosity or nebula. So this is very important in scientific research. So this needs a special spectrometer, and we need a special software for this also to analyze this the absorption spectra. But you don't have a telescope. Many have a telescope, but everyone do not have a telescope. So don't disappointed. Don't be you can go through the website universe.org. There will be several projects, not only the in astronomy. There will be a biology project. There will be a chemistry project. A lot of projects there, and these are scientific projects. You can perform through your laptop, through your computer, and you can give a scientific report to this website through a proper process. And there this if you uh, done the good job, then they can publish in their website or journal. So this is a very easy and very scientific, very much scientific for the enthusiast. Another website is the asteroid search program, international asteroid search campaign. So just visit also iasc.cosmosearch.org, and this gives you a there should be just a process. You have to mail this uh, instructor director for the campaign, and you can perform, and this gives a good result. This is a another citizen science program, and anyone can perform this program through rad@homeindia.org. Professor Ananda Hota is a director or instructor of this project. This actually this is the data from coming from GMRT, Giant Meter Radio Telescope, the global giant telescope, biggest telescope, radio telescope. So you will just trying to do scientific research. So no problem, just go visit this site, and there will be a lot of process. You have to give the training through Facebook or any other group meeting, and after training you will be able to do some RGB analysis. So after your performance, there should be e astronomer certificate, and we will be grateful just like astronomer. So this is very much important and very much scientific citizen science program, and you are also a chance to visit our this GMRT telescope site. So this is a very much opportunity. Those who have no scientific communication, scientific engagement, just like you are a teacher, you are a just a science lover. So you go through this website and go through the scientific experiment.